Our next lecture in Chapter 5 is on conditional probability and the general multiplication rule. Our first objective is to compute conditional probabilities. A conditional probability uses the notation P f of E and is read as the probability of event F given event E. It is the probability that the event F occurs given that event E has already occurred, okay? The probability of F slash E is read the probability of event F given the event E. So we're looking for the probability that F will occur knowing that E has already occurred. So let's look at an example. Suppose a die is rolled, a single die. What is the probability that the die comes up 3? Now suppose that the die is rolled a second time, but we are told the outcome will be an odd number. What is the probability that the die comes up 3? Well, the first roll is really straightforward, right? This is just our simple probability calculation, which is the number of events in the outcome, which is just 1, the number 3, over the number of outcomes in the sample space, which is 6. So the probability of rolling a 3 is 1 out of 6, or 1/6. The probability of the second roll, now we know that the second roll is going to be an odd number, so the sample space is smaller. It's only 1, 3, 5. And so that the probability of rolling a 3 from this sample space is, again, there's one outcome, the number 3, and there were 3 different possibilities in the sample space, so this outcome is 1/3. Notice that the conditional probability reduces the size of the sample space under consideration, and the conditional probability here was that the outcome is odd. And in this case, it went from 6 outcomes to 3 outcomes. So the conditional probability rule states that if E and F are any two events, then the probability of F given E is the probability of E and F divided by the probability of E, okay? What this simple, let me read this again, sorry. The probability of event F occurring given the occurrence of event E is found by dividing the probability of E and F by the probability of E, or simply by dividing the number of outcomes in E and F by the number of outcomes in E. And so that's the simplified formula. So the probability of F given E in the numerator is the number of outcomes of E and F divided by the number of outcomes for just E. All right? So let's look at an example. The data in Table 8 represent the marital status and gender of the residents of the United States age 15 or older in 2017. We can see the different marital status: never married, married, widowed, divorced, separated, and then the totals in each. And then we separate by males and females, and of course then the totals for never married, married, etc. And then the totals at the bottom here are for all the males, all the females, and then the total population. Okay, so question A, compute the probability that a randomly selected individual has never married given the individual is male. Okay, so remember in the numerator is the combined the probability of never married and male, or specifically when you're having observations, you can just count the number of observations or the number of outcomes. And so the number that is never married and male, so we go to never married and male, which is this first cell. So our numerator is going to be 46. The denominator is the event that is given the individual is male. And so we're looking for the total number of males in the survey, which is 126.9, and that is our denominator. Again, the combined number of outcomes or the combined probability divided by the number of outcomes in the second event, the given event. And so 46 divided by 126.9 gives us a probability of 0.362, so about 1 in 3. Let's flip this around, and I like this problem because this is a confusing formula, to remember what goes in the numerator and what goes in the denominator. The denominator more, the numerator is the combined, but do you put the first event or the second event? And remember, we put the second event, the given event, in the denominator. So now we compute the probability that a randomly selected individual is male, given the individual has never married. So we have the same two events, but in reverse order. So because we have the same two events, the numerator is going to be the same, because remember, the numerator is the number of outcomes that are both male and never married. So that's still 46. But the denominator now, the given event, is that an individual has never married. So we're looking for the number of total responses of never married, which is this top row here. And we can see to the right, that's 86.1. So our probability of male given never married is 46 over 86.1, which is actually 53.534, which is a much higher percentage. This is 1 in 2, almost more than half of the population, or more than half of the never married people, the non-married people that have never married, more than half are going to be male. Okay? So again, remember here the formula, the probability of F given E is the probability of both of them, E and F, or specifically the number of outcomes or observations of both E and F, the event that's E and F, the intersection, in our case males and never married, divided by the number of outcomes of the given event, which is the second event, so the number of outcomes of E, and in this case it was never married, which is here. Okay, so again, make sure this formula is in your head and that you have some way of memorizing it. Suppose that 12.7% of all births are preterm. The gestation period of pregnancy is less than 37 weeks. Also, 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. Okay. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? Okay. So we're looking for 8 pounds and preterm. Well, notice that's the 0.2%. Tells us all births resulted in a preterm baby. 0.22% of all births resulted in a baby who weighed 8 pounds. So that's preterm and 8 pounds or more. Okay. So that's our numerator. Our denominator is preterm, given that the baby is preterm, and 12.7 of all births are preterm. So that's our denominator. So here we get 0.0022. Be careful there. 0.22% is not 22%. It's 0.0022. It's not, okay? It's 0.22%, which means we have to move the decimal place 2 more places. So this is also a good kind of mental check. Be careful with percents, because sometimes when they're decimal percents, we forget to move the decimal again another 2 places. Just as we did with the denominator, which is preterm, 12.7% is 0.127. Okay? So this gives us a probability of 0.0173. So what do you think? Is this unusual or quite common? Well, 0.0173 is almost 2%, right? Almost 2%. But this is 2% of all of the babies. This is 0.2% of all of births. I'm not saying this wrong. Let me slow down. 0.0173 is equivalent to 1.7%. So 1.7% of all births are preterm with a baby that weighs more than 8 pounds. So that is quite unusual. I mean, it's a very low percentage. 1.7% is not a high percentage, right? And that kind of, it actually makes kind of common sense, right? With preterm babies, they're usually underweight. They're certainly not, 8 pounds, 13 ounces is a big baby. So I don't know what that mother was eating. All right, let's move on. So if 100 preterm babies were randomly selected, we would expect about 2%, 1.7%, to weigh 8 pounds, 13 ounces or more. This is an unusual outcome. Unusual, how do we know it's unusual? Because the percentage or the probability is low. It's 0.01, okay? So 0.017, so less than 2%. Our next objective is to compute probabilities using the general multiplication rule. The probability that two events E and F both occur is the probability of E and F, that's that both E and F both occur, is equal to the probability of E, the first event, times the probability of F, the second event, given E, okay? In words, the probability of E and F is the probability of event E occurring times the probability of event F occurring given the occurrence of event E, okay? And we know how to do this, right? The numerator is the combined outcomes and the denominator is the second outcome. All right. So let's look at some more examples. The probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? Okay. So the probability of a driver who is speeding gets pulled over and gets a ticket is equal to the probability of E and F, assuming that E is a driver who is speeding and gets pulled over, and F is getting a ticket, okay? So the probability of E, that a driver who is speeding gets pulled over, is 0.8. The probability of that a driver gets a ticket, given that he or she is pulled over, this F given E, is 0.9. So we multiply those two probabilities up here and we get 0.72. Okay. So the one thing that I didn't do here, we should have assigned these as E and F. E is the probability that a driver who is speeding gets pulled over. So you might say E is pulled over and F is gets a ticket. Okay. The probability that a driver who's speeding gets pulled over and gets a ticket is 0.6. All right. Let's look at something called acceptance sampling. Suppose that 100 circuits sent to a manufacturing plant, suppose that of 100 circuits sent to a manufacturing plant, 5 are defective. Okay, so 5 out of the 100 are bad or defective. The plant manager receiving the circuits randomly selects 2 and tests them. If both circuits work, she will accept the shipment. Otherwise, the shipment is rejected. What is the probability that the plant manager discovers at least one defective circuit and rejects the shipment? Now remember, when we have these inequalities, at least, at most, we have to think in terms of exactness. So what does at least one defective circuit mean in terms of this problem? Well, she's selecting 2 and testing them, so at least one means that 1 is defective or 2 is defective. It can't be 0 is defective because that's what we're looking for, okay? If 0 are defective, she won't reject it, she will accept the shipment, okay? Of the circuits, 5 are defective, so 95 are not defective or are good. The way we want to do this is because there are all these different combinations depending upon the order. So we want to construct a tree diagram to determine the possible outcomes for the experiment. We did a tree diagram, I believe back in chapter 3, with families that had 3 kids and what gender they were. You might remember the first kid was either boy or girl, and then each of those, the second kid was boy or girl, and then the third kid was boy or girl in each of those. So you had like boy, 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 girl, boy, boy, girl, girl, etc. And so that's what we're going to do here as well with these two circuits. Now, each circuit is either good or bad. So it's really similar to the gender problem where it's boy or girl. Here we have good and or defective. Okay? So in the next slide, we're going to look at that tree diagram where D stands for defective and G stands for good or not defective. And because the outcomes are not equally likely, we include the probabilities in our diagram to show how the probability of each outcome is obtained. Remember, we multiply the individual probabilities along the corresponding path in the diagram. Okay? So she pulls out the first circuit, and it's either good or bad. Well, if it's good, remember it has a probability of being good of 95 out of 100 because 5 out of the 100 were defective. Okay, so those are those probabilities. Now the second circuit that she pulls out, if it's good, now we have the probability of the second one being good. Now the first one was good, so we take 1 out of the good, so the 95 becomes 94. And we've also taken 1 out of the 100 because from that first circuit. So that also drops. So the probability that the second is not defective or the second is good is 94 out of 99. Okay, I'm going to continue along this path. And so the probability that both are good is 95 out of 100, the first probability, times the second probability. Okay, 0.902. If we veer down and the second circuit is bad, right? Well, here we've taken one circuit out, so the denominator is only 99 now because we've already picked one circuit. But the first one was good, so there's still 5 left out of the 99. So that's the probability here. So our probability of having a good first circuit and a bad second circuit is 95 out of 100, the first probability, times 5 out of 99, which is 0.048. If we follow when we pick the first circuit, it's defective or bad, notice the probability of that is 5 out of 100, and that was given in the original problem, that 5 out of the 100 were defective. Then we get to the second circuit. Okay, if it's good, notice this is we've already used one circuit, but it was bad, so the denominator becomes 99, but there are still 95 left that are good. So we have a 95 out of 99 probability. So our probability of defective good is 5 out of 100 times 95 out of 99, which you see here. And then finally, the last branch of the tree is defective, defective. Okay? So we pulled one defective here. Now we're doing another defective. So we've already pulled one circuit, so that drops by 1. We've already pulled one defective one from the first circuit, so the numerator also drops by 1, and so we get 4 out of 99 for the combination of defective, defective, and we multiply them, we get 0.0002. So the probability that at least one is defective, all we have to do is look through here and look for any of these options that have a D in them. So we have GG, that's not one, GD, DG, and DD. So this is 1 defective, this is 1 defective, and this is 2 defective, which is also included in at least one or more. And so we simply add all those probabilities of 0.048, 0.048, and 0.002, and we get a probability of 0.098. So that means that about 10% of the time, 0.098 is 9.8%, about 10% of the time, the manager is rejecting the package. The probability that the shipment will not be accepted is 0.098. So about 10% of the time, they are rejecting the package. They're not accepting it. Now, we can do this problem in a different way. We can compute the probability that both circuits are not defective. Notice in that tree diagram, we had 4 options: good, 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 defective, defective, good, and defective, defective. There was only one option where they were both good. So if we calculated the probability that both circuits are not defective or both circuits were good, we could then use the complement rule to determine the probability of at least one defective. Well, the probability of at least one defective would be 1 minus the probability that none are defective. And this would be 1 minus the probability the first is not defective times the probability the second is not defective, given that the first is not defective. Okay? So we had both of those probabilities before, that the first is not defective, so that was good, 95 out of 100. And the second was not defective. Well, we used one good here, so we lose a number in the numerator, we lose a number in the denominator, lose one in the denominator, and we multiply this through, and we get 0.902. And then remember, this is the complement, so we subtract that from 1, because remember, all of the probabilities for each outcome in the sample space has to add up to 1. And so since we had 3 out of 4, we're just taking this last case and figuring that out. The probability that the shipment will not be accepted is 0.098, and you see here that we got the same result. So this is just using an alternative method, and hopefully that helps you build kind of an insight around the concept. So let's look at another example, a favorite other. In a study to determine whether preferences for self are more or less prevalent than preferences for others, researchers first asked individuals to identify the person who is most valuable and likable to you, or what they call your favorite other. Of the 1,519 individuals surveyed, 42 had chosen themselves as their favorite other. And here's the source information. Suppose we randomly select one of the 1,519 individuals surveyed. What is the probability that he or she chose himself or herself as their favorite other? Well, this is a simple probability, right? 42 people chose the outcome of themselves, and the total sample space, or the total number of observations, was 1519. So 0.02765 is the probability, or about 2.7% of the population, or this sample, selected themselves. If 2 individuals from this group are randomly selected, what is the probability that both chose themselves as their favorite other? Okay. So we could do the same kind of tree diagram again, and in this case we're looking for themselves, I guess you would say, versus other, so I guess TT instead of OT or TO or OO. Okay. So remember, the probability of E1 and E2 is the probability of the first one times the probability of the second one given the first one. Well, the probability of the first one, we've already figured out that the first outcome is selected other. And this is similar to the second approach, where, okay, if the second one is also selected other, well, then we've taken one other out of the initial population. We've taken one observation out of the total, and so we have 41 out of 18 is the probability that the second one will also be other, and we multiply these, and now we get 0.000746. Notice this is 0.074%, so a very, very small percent. Compute the probability of randomly selecting 2 individuals from this group who selected themselves as their favorite other, assuming independence. The assumption of independence means that the outcome of the first trial of the experiment does not affect the probability of the second trial. Okay, they're not conditional. We are assuming independence. The opposite of conditional is independence. that the first case has no impact on the second case. It's like sampling, but with replacement. The last example we did in the alternative approach used sampling without replacement. As soon as we took a circuit out, as soon as we took an observation out, we decreased the size of the sample for the second drawing, if you will. Therefore, we assume that the probability that the first person chose themselves is equal to the probability that the second person chose themselves, which is just our general probability. 42 people selected themselves out of 1519. So the probability of of E1 and E2, or both people selecting themselves, is simply the product. This is the multiplication rule, the product of both of those, the product of both of the probability of each event, which gives us 0.000765. It's not very different. The difference between replacement and not in this specific case is rather small. And so finally, this idea of the independence of events, if small random samples are taken from large populations without replacement, it is reasonable to assume independence of the events. Okay? So if we take a random sample, if we take a small sample from a large population without replacing them, we're assuming independence. As a rule of thumb, if the sample size is less than 5% of the population size, we treat the events as independent. Something for you to kind of stick in your mind there. It's there, bold in yellow. So if a sample size is less than 5% of the population, we treat the events as independent. And as we saw in the last one, because it was such a small difference, that's why we can do that, because it's going to have a smaller impact in the final probability calculation. Two events, E and F, are independent if the probability of E given F is just equal to the probability of E, or equivalently, the probability of F given E is simply equal to the probability of F. So this is telling you that the probability of F given E, the given E has no impact on the probability of F. Okay?